Atoms, they're so tiny, we can't even see them. But we know they exist, and we know they have a nucleus, we know they have electrons, and we know a few things about them. So in this topic 7, nuclear physics, we're going to discuss how we know those things about the atom. We've got a model, but there's some limitations to it, and we're going to talk about the evidence of how we know these things. Now, look what I'm going to do. I'm going to draw a nucleus here with some protons and neutrons in it, and then I'm going to draw some crazy electrons orbiting around here. Now, this isn't really what an atom looks like, but it's not the worst model ever. In the late 1800s, no one had any idea, even your smartest person didn't know that this was a reasonable model of an atom. And a few things that you need to know about this model is that the nucleus, oops, I can spell it right, which is right here, is tiny relative to the rest of it, is incredibly dense relative to the rest of it, and it is positive. You might be thinking, duh, I learned that in middle school, but let's make sure we still know. Zipping around here are these electrons, and they're not really going in circles like planets or anything like that, but they are on the outside, and the area where they go accounts for most of the volume in our atom, and they are negative. One electron is equally negative to the magnitude of the charge of a positive proton. Now let's go through some of the models historically that people thought about atoms. In the late 1800s, people were hungry and they were into desserts. And so there was a dessert called plum pudding, which if you see a real picture of it, Google it, it looks disgusting. But it's like a cakey thing with little raisins or plums. No, there's no plums in it. It's like raisins. And people thought, well, we know electrons exist because they had discovered those. And they thought, well, if we've got electrons, which are little negative particles, then the rest of the stuff must just be this light, fluffy, positive goo. So let's make this a different color. Let's say we've got this positive goo. Sorry, why can't I turn that black? There we go. This positive goo around here. And they thought if they shot something small and positive, like an alpha particle, which kind of looks like a fish, they thought it would just go straight through there because it's going through some not dense stuff. But then Ernest Rutherford, who was a Kiwi from New Zealand, funny enough, built this device. And you can think that it had an alpha source shooting these alpha particles, which are small, positive, dense helium nuclei, at gold foil. Why gold? I don't know if he had a bunch of gold lying around, but he did it. Or maybe his assistants, Geiger, famous for the Geiger counter in Marsden there. And he shot it at the gold foil, and 99% of them, or a lot, went through and hit the screen over here. But a few of them bounced off at these crazy angles. And he was like, whoa, if we just have light positive goo, I can't shoot something dense and positive and energetic fast and expect it to bounce off at these crazy angles and hit this screen that he had around here. So what we end up with, since that happened, was what was called the Rutherford model, where they knew that since this alpha particle, which is positive and dense, it hit something and bounced off at crazy angles, it must have hit something that is positive, like this nucleus, and dense. So all the mass of an atom must have been concentrated at the middle. And so if you want to zoom into what was happening in this gold foil experiment or the Geiger-Marsden experiment, most of these alpha particles, which again, we use an alpha symbol, most of them went through, and most of them went almost straight through. But a few of them went off at these crazy angles because they got next to this gold nucleus. It's a way of doing an experiment to see what something looks like when you can't really look at it. So let's say I take something clever, like a prism. I'm going to draw an awesome prism for you right there. Oh, that's a nice prism. And you hold that up towards the sun, you're going to get this pretty rainbow here that's going to say a little bit of Roy G. Biv action backwards with your low energy end and your high energy end of the spectrum. Or you could use a spectroscope, which is a more clever device. Now, if you take, let's say, a glass tube and you fill it with some hydrogen gas, which would be an H2 form, and you electrify it, and you give it energy, you won't get that whole pretty rainbow, even though it will glow. If you looked at it with a spectroscope, which is kind of like a fancy prism, you're going to get these very distinct bands, a few wavelengths of purple, one wavelength of blue, and maybe one of orange. This is an emission spectra. And what's happening is these electrons who are just hanging out in their low energy state suddenly are like, wow, and they fly up a level. And this guy's like, wow, and he flies up a level. And this guy doesn't have anywhere to go. This guy's like, wow, and he flies up a level. But then, because they absorbed energy, they drop down. And this guy drops down. And as they drop down, they give off these very particular, or they emit these particular wavelengths of light. And each element has its own very specific pattern of emission spectra that it gives off. What we just talked about, you can consider an emission spectrum. Emission, because it's emitting radiation. Sort of the opposite of that is what we call an absorption spectrum, where the electrons are going to be sucking in radiation. And what you get is you get a nice, pretty rainbow here for your absorption spectra, but you are missing a few key wavelengths of light. And it's like if you had a big jar of gas and you filled it with hydrogen and you let a lot of white light. I'm writing about white light in black marker for the irony. And what's going to happen is these electrons, as light comes through, they are only going to absorb a few key wavelengths, and they're going to jump up. Now maybe they'll fall back down. I'm not sure what happens. Maybe they give it off as a different wavelength or something that you don't notice missing. But anyway, what happens is they let the vast majority go right through, and you get this whole rainbow up here. But you get a few missing. And again, each element has its own specific absorption spectra, which is cool because we can take the light coming from a star that is 100 light years away or more, and we can analyze its absorption spectra. And even though we could never ever visit that star, we know, oh, that star is made of some hydrogen and some helium because we're looking at its particular absorption spectra. Pretty sweet.